ahead, if you would. This is actually, I have no idea what year it is. I think it's 2001, maybe. This is a free response question from 2001. It's either 2000 or 2001. And what you should see there is you'll see two steps for a reaction. And the first one, it tells you it's an environmental concern, is the depletion of ozone, where O3 is normally in equilibrium with O2 and O. A proposed mechanism from the depletion of O3 in the upper atmosphere is shown below. So you have the overall, the two steps for this equation. What you're not given is the overall, but that's okay, because how do you think you can make the overall equation from this? What do you think you need to do? Anyone? Hello? How do you make the overall? Well, I can't find the rate law because I don't have enough stuff. But what did I tell you yesterday was the first criteria for a mechanism? What now?
Is it like slowest rate?
No. Go back and look what you had yesterday. Somebody who's got it right handy. What was the first thing I said was part of that you had to have for a mechanism to be? The steps have to add up to give you the overall reaction. Okay? The steps have to add up. All right? So, I'm going to put myself a little line here, and let's cross things out that we can cancel out. So, what can I cancel? Okay, the CLs are gone. What else? CLO. Anything else? No. So, let's write what's left. O3 plus what? O yields O2, and how many O2s are there? There's two of them. So we can put 2O2. So there you go. That's not too hard, is it? Okay, pretty simple. We just did part A. So I'm going to put a little check. We did that one. All right, the second one here says, clearly identify the catalyst in the mechanism above and justify your choice. Okay, so tell me what the catalyst would be. What do you think the catalyst would be? You can go back, and I can probably erase what I just did right there so you can see. All right. CL, is CL a catalyst? Okay, let's see why it would be a catalyst. It is a catalyst, but let's figure out why. Okay. It is, whoops, CL, because, okay, it is there initially. It is present initially. And cancels out. I'm going to run out of room, so I'm going to put it out here. It cancels out at the end. Okay, that's how you know. All right, that's it. CL is going to have to be your catalyst. Okay, now if you look at the next one, it says clearly identify the intermediate. Let me go back and let me make it so the slide so I have more room to write. What would your intermediate be? All right, CLO. Now let's say why CLO would be your intermediate. Why would it be your intermediate? It's produced in one step, and then what else? And used up or consumed in another. Does that make sense? That's it. All right, now, so far so good. It's not too difficult of a question. It's pretty easy, to be honest with you. So let's look at part D. It says, if the overall rate law is found to be rate is equal to K times O3 times CL, determine the following, the order of the overall reaction. That's super easy because they just told us the rate law. What would it be? Second order. Does it say we have to describe why? No. Okay, now it says on part 2, give appropriate units for K. So what that means is if I go back, I'm going to do it up here because I just don't have room, so I'm going to write it here. Rate equals K times something else. Is that correct? But they're both molarities. Now, rate is always molarity per time. Now, you can do it per second or you can do it per minute. Doesn't matter which. Does it say up there? It doesn't give you anything, so you can just do per second. So if that's the case, if rate is molarity per second and it's a second order reaction, what would the units be? 1 over what? 1 over m times s. So you can do 1 over ms or m to the minus 1, s to the minus 1. What was the other one we did? Or liters over moles times seconds. Any of those are fine, okay? So far, we've done everything, and none of it has been hard. For part 3, it says determine, or the rate determining step of the reaction. So we have to determine what is the rate determining step. So go back and let's look at the steps. I'm going to come over here. What is the rate law for step 1? Rate equals what? K times O3 and then CL. What is the rate law for step 2? Now you cannot have the intermediate in there, so it's rate is equal to K times what? It's going to be O3, right? CL, and then what else? And then finally O. All right, so now that we know those two rate laws, what's the rate determining step? Step 1 or 2? Step 2, excuse me. Step 1. So when it says the rate determining step, here's what we're going to say. We're going to say it's step 1 because the rate law of this step, whoops, how do I undo that? I don't know. This step matches the experimental rate law. Because the experimental rate law was rate is equal to K times O3 times CL. Does that make sense? I know it does. I know I'm not used to this yet because I know it says Doceri desktop trial. It's because I'm not paying for it yet because I got to decide if I like it. I'm not 100% sure I do. So it's step 1 because the rate law of that step matches the experimental. That's pretty easy, right? That's not hard. Okay, good. All right, let's go ahead, and if you want to, you can either, I forgot this piece of paper is blank on the back. You can either write on it or write on the other sheet of paper that you have. But I want to give you some other information in terms of what we're going to need to do when we look at rate laws, okay? So there's a couple of things that I want us to do. You can either have the data and experimentally determine the rate law, which is what we've been doing, or sometimes you have a situation where you only have one reactant, okay? So if you only have one reactant, it's not quite as easy, okay? So what we have to do here, that's not how you spell that, Reeves, react. One reactant. Did that not show? Oh, why did that show up way down there? Sorry. Y'all just be patient with me. Because I don't know what I'm doing. Go back. Hold on. Not that small. There. Okay. It's because it's a blank space and I can't tell where I'm writing. All right, so if it has one reactant, if we graph this is the way that we would graph it. We would start and we would try to graph the concentration of A versus the versus time, okay? Now, if we were to graph that and we get a straight line right off the bat, if we get that, that means that this is zero order, okay? Zero order. That means that the rate law would be rate is equal to what? K. So K is the rate. Let me tell you what K is also equal to. K is equal to the negative slope. And the reason I have to say negative slope is because if you look at that line, it has a negative slope. K cannot be negative, so I have to say K is equal to negative slope. So if the slope is negative and I say negative slope, negative times negative is positive, okay? Now, if we, and this is where you're going to have to hang tight because I'm going to draw several graphs. If we do this, if we graph it, and we're actually going to do this tomorrow, I think. If we do this and we do not get a straight line, let's say we get this. Okay, that's not a straight line. Then our next step is to graph the natural log of the concentration of A versus time. Okay? If at that point we get a straight line, then we say that this is first order. Okay? And that means rate is equal to K times whatever A is. And you can put a 1 up there if you want to. Raised to the first power. Okay? What that means also is slope is equal to negative, whoops, let me go back. I don't want to say slope is equal to. I want to say K is equal to negative slope. Again, you have to negate it, okay? Now, if in the event, I'm going to start drawing smaller so I can fit it. If I graph it and I get this, that doesn't work. If I graph ln time and I still get that, I don't get a straight line, I have one other option. And the other option is to do, that should have been ln of A, by the way. Then I have to do 1 over the concentration of A. If I graph 1 over the concentration of A versus time, I'll get a straight line, but the slope is positive. Okay? So, when I come over here, that means, and let me put a line over here that these all go together right there. This means that it is second order. That means rate is equal to K times A squared. And then I know I don't have room right there, so I'll write it over here because the little desktop trial is in the way. What would K be equal to this time, you think? Positive slope. K equals the slope. Okay? Now you may say, well, what about, okay, we got 0 first and second. What about third, fourth, and fifth? One reactions only fall into the category of 0, first, or second. So you won't have to deal with that. You'll only deal with 0, first, or second. And the reason that we have to do it graphically is because we can't do what we did with the others, where we would hold something constant, okay? So we can do it graphically rather than doing it the way that we did yesterday. All right, now having said that, let me go ahead and give you the integrated rate laws. Now the integrated rate laws are in your packet that has the other information, but I want to give you the integrated rate laws. Now the reason you use the integrated rate laws is because you can use them to find a couple of other things. Okay, so the integrated rate laws. Now let's make a little chart. Again, that's in the middle, sorry. Let me fix that. I need a bigger eraser. There we go. All right, so let me pull it back down so I can see. This is the hardest thing to get used to. So integrated rate laws. All right, so let's start first of all with zero. All right, here's the zero order. The zero order integrated rate law looks like this. It is the concentration of A, and it actually doesn't have, when you look in the formula packet, it doesn't have an F there, but it means final, minus the concentration of A with a little zero. The zero means after times zero, okay? Times zero. So, uh-oh, did it go away? Wait a minute. Sorry. That means after no time has passed. So that means initially. So you may want to put yourself a note that says initially. That should say initially. Oh well. And then it's equal to negative KT. Now I'll double check. It used to be that AP didn't give you these formulas, but I think they do now, which is good. So it's the concentration of A minus the initial concentration of A is equal to negative KT. If it's first order, then it is the natural log of A minus the natural log of A initially, 0, is equal to negative KT. Why do you think it's negative KT? Right, and remember the first two, 0 in first order, if you go back and we look at, I'm going to attempt to go back, there we go, their slopes were negative, weren't they? So that's why it's negative KT. Now when we go and we look at second order, you should be able to expect that it would not be negative, it would be positive. And so this one is 1 over the concentration of A minus 1 over the concentration of A, 0, equals positive KT. Now the reason we have the integrated rate law is we use the integrated rate law to find a concentration that is not found in our data table, okay? And we may not have it in our graph. So that's why we use the integrated rate laws. You will only use that if you're asked about how long something takes, or if they give you an initial amount and ask you what it would be after 25 seconds or something like that. Then you can use these problems, and I'll tell you which ones correspond to that in just a moment out of your book. But those are the integrated rate laws. And I know, Camille, you asked about the half-life. Didn't you ask me about half-life on one of them?
Yes, ma'am.
But that was you were looking at the wrong question. You were looking at the wrong one. But you also need to know the half-life formulas. Now, for us, half-life is going to be a little bit different than we did in regular chemistry last year. You actually have a couple of formulas that you'll follow. So I want you to jot these down too. The half-life formula. Now, AP only gives you one of them, which means they'll only ask you to use them for that particular order of reaction. Half-life formulas, and this is what they look like, okay? If you have a 0 order, it's all done by the orders. 0 order, it is T1 half is equal to the concentration of A initially over 2K. That's your half-life formula for the zero order reaction, okay? Zero order. All right, now for first order, it's a little bit different, and this one is on the AP formula sheet. T 1/2 is equal to 0.693 over K. And in order to do that, you would have to have your K value, and you would need to plug that in. And then finally, for second order, you can write second order, but I'm not going to have room because of that little thing in the corner. I'm going to just write it out for you. T 1/2 equals 1 over K times the concentration of A, but it's the initial. And again, let me put myself a note here so you remember that that means initial, or when no time has passed, okay? And the other one can be any point after time has passed, okay? And that's all there is. That's all there is to that, okay? Now, if you'll look at the back of your, or if you look at your formula packet, I'll tell you which one, not formula packet, but your book problems. There are certain ones that are in there. Now, here's the thing. They don't give you a graph, but let me just read it to you so you can kind of see what I'm talking about. What you have to do is it will tell you, let me find one. It tells you what you're graphing, and it will tell you what the graph resembles. It will say that you graph natural log of whatever it is, and you get a straight line. Well, based on that, you're able to determine, okay, well, since it was natural log and it was a straight line with a negative slope, that means it's first order, okay? So you don't have to actually see the graph. They're going to tell you what the graph looks like, okay? What we're going to do, though, and I think we're going to do it tomorrow. I forgot regular chemistry's in there on Friday, so can we do the lab tomorrow? She brought all the they brought all the equipment. Is that good? Are y'all good for lab tomorrow? So we'll do the lab and actually graph it ourselves and see what order of the reaction it is based on the graph, okay? Based on the graph. So there's some in the book that work that way. Let me show you one other quick thing, and I just want to show you where this is in terms of the graphs are concerned. Let me add one more thing. Remember how we had the graphs that were like this? And I did something like this. Y'all see what I'm talking about? Okay, I need you to understand that the activation energy is always in reference to where the reactants are. Even if I do it this way, and I start up like this, it's always in reference to where the reactants are, okay? So from here to here, and from here to here, okay? That's going to be your activation energy. Now, I already told you that this was what? Your intermediate, right? Didn't I tell y'all that yesterday? Okay. If I said you used a catalyst in step 1, or actually step 2, let's do step 2, because the second hump would be step 2. If I used a catalyst and I said draw on that graph how the graph would change if you used a catalyst, what would you do?
The hump would be shorter.
Okay, the hump would be shorter. You wouldn't change anything else, okay? That's it. And as far as which step is the rate determining step, it's going to be the one that requires the most activation energy, because that's going to determine it, okay? So, does that make sense? All right. If you would, go ahead and take that worksheet out from yesterday. And I know y'all don't have your books, but I'm going to go ahead and I'll put it on the screen if you need it, or if we need to